Ladies and gentlemen, good evening and welcome. Thank you very much for coming to this, the Society's 6th London lecture for 2014. My name is Mike Young. I'm a geophysicist with the BGS and I'm a member of the Council of the Society here. And it's my pleasure to introduce today Dr. Matthew Genge, who's going to speak to us about geology in space, meteorites and cosmic dust. And so far in this series, and I'm sure many of you have come to the previous ones, we've heard lectures on some of the terrestrial issues where geology and geologists contribute, particularly on energy, on nuclear power and radioactive waste, and on the management of contaminated land. But geologists are not only concerned with Earth and with Earth rocks. Tonight we're going to be more exotic. We're going to reach out into space, look towards other worlds. Rocks are found, of course, throughout the universe, on other planets, on asteroids, meteorites, comets, ranging down to the smallest piece of cosmic dust, in fact. And studying these rocks tells us much about the origin of our own world. So it's a great pleasure to welcome Dr. Genge tonight. He's a very distinguished planetary scientist and geologist, and he's going to discuss the geology of space, if you like, as recorded in meteorites and cosmic dust, demonstrating that the principles of geology hold true far beyond our own planet. He has been a senior lecturer at Imperial College at the Royal School of Mines since 2002. Previously he worked in the Meteorites division at the Natural History Museum, and he's also an advisor at the National Near-Earth Objects Information Centre. And you've probably seen him frequently on TV whenever meteorites make the news. He's also served on a NASA committee concerned with the collection of cosmic dust and worked on the NASA's Stardust program to collect rock samples from comets. And in recognition of some of this work, he's actually had an asteroid named after him by the International Astronomical Union. It's called 6626 Matt Genge, and perhaps he'll tell us something about it. Ladies and gentlemen, please welcome Dr. Matthew Genge.
Thank you. I was told I don't own the asteroid, but I'm also not responsible for any damage it does. It's pretty good. So what I'm going to talk about today is meteorites and cosmic dust, so rocks from space. Now, I was told that this is a public lecture, so apologies to any retired geologists, people who might have taught me at university. This will be aimed at the general public, but I will throw some more difficult stuff in there as well. The main thing I want to consider really today is this geology? So I'm going to be talking about rocks from space, but can we apply the term geology and the principles of geology to studying meteorites and cosmic dust, to studying rocks that form beyond our planet? Because if you look up geology in the dictionary, this is the definition you'll find. Geology is the study of the Earth. It usually frequently says the study of the solid Earth, surface processes, and how those affect the rest of the Earth system, the hydrosphere and atmosphere and biosphere. And of course about Earth history, and let's not forget good old Earth resources. No mention of other planets, certainly no mention of space. So the question is, does geology apply to rocks from space? Because they fall all the time, and we had a reminder of that process last year. So in February last year, a meteorite entered the atmosphere over the Russian city of Chelyabinsk and exploded with an energy of 500 kilotons. So you put that in perspective, the Hiroshima bomb was 10 kilotons. So this was considerably more powerful than that nuclear weapon. The shockwave from this event spread out across the city, broke loads of windows, injured 1,500 people, but luckily nobody was killed. And the event dropped 654 kilograms of meteorites. Now this is one of these Chelyabinsk meteorites, and you can see surrounding the outside of this rock, this very thin, black, shiny crust. This is one of the key features of meteorites. It's a fusion crust. And it forms because of the intense heating it goes through as it comes through the atmosphere. You'll notice actually that that fusion crust is really, really thin. It's less than a millimetre thin. That's largely because the magma that's produced is actually pulled off of the back of the meteorite as it's coming through the atmosphere. Now, this isn't obviously the first time that meteorites have fallen. They've fallen all the way through Earth history. And even the ancients knew that occasionally rocks fell from the sky. So this is the Temple of Apollo at Delphi. And it used to house the stone of Aphrodite, which they believed was cast from the moon by the gods. So this was a meteorite. This was a rock that fell that somebody saw falling out of the sky. And they obviously attached some religious significance to that. But not everyone at the time believed that these were religious events. So Aristotle actually had a theory about how meteorites formed. So he said that meteorites, these rocks that fall from the sky, condensed from Earth gases. Gases were escaped from the Earth. They condensed into a rock in the sky, and then that rock fell back down to Earth again. Now, the reason that Aristotle didn't believe that these came from space is he had a theory about space, about the universe, where the Earth was at the center, and surrounding the Earth were these perfect celestial spheres, each one containing a celestial body. So obviously the moon was first, and then all the planets, and then in this outer celestial sphere were the fixed stars. So to Aristotle, there was no room in this perfect universe for these awkward bits of rock that occasionally ran into the Earth. And that thinking actually pervaded science all the way up to the Age of Enlightenment. And meteorites really weren't believed to occur at all. Rocks weren't thought to fall from the sky, right up until this chap came along, Ernest Chladni. Now, he's German. He worked in Leipzig, and he did the very first systematic scientific study of meteorites. And what he did was he interviewed people who said they'd seen a rock fall from the sky. He collected all these witness statements, and then he identified the similarities in all these statements. And he argued that without collusion between these people, the similarities meant that these events must happen, and he suggested they must come from outer space, from beyond the bounds of our world. And of course, he was absolutely correct, and therefore was ridiculed by the rest of the scientific community, as we know happens so frequently. But an event was just about to happen when he published this paper, which would change all of that. Because that year, there was a shower of stones in Siena, in Tuscany, in Italy. And Tuscany, Siena in particular, was on the Grand Tour. So if you were a lady or gentleman of breeding at this time, you would go on the Grand Tour of Italy. And so English lords and ladies observed rocks falling from the sky. And who is more believable than an English person with a title? And so it was immediately recognized that, yes, these events do happen. We need an explanation. Then came another coincidence, quite a remarkable coincidence, actually. Vesuvius erupted 17 hours before the fall of the Siena meteorites. And this chap, Lord William Hamilton, who was the husband of the infamous Lady Hamilton, he was a naturalist. He was living in Naples. He had observed the eruption, and he suggested that the fall of meteorites, they were ejected from Vesuvius. And he was shown a piece of the Siena meteorite, and he stated that this was identical to those rocks that I've seen on Vesuvius, which kind of sounds like my first year students, actually. And there the matter might have just laid to rest. Everybody might have believed that rocks that fall from the sky are ejected from volcanoes, except something else happened. The very next year, in the UK, in Yorkshire, another meteorite fell. At a little town of Wold Cottage, and by the way, we name meteorites after the nearest town to which they fall. And as you can see, being Yorkshire, they named a beer after it. But the significant thing was, it fell just outside the land of this Major Edward Topham. And he was a well-known figure in London because he was the proprietor and the editor of the World newspaper, which was famously known as one of the most scandalous newspapers in London, because it mainly reported on divorce and affairs. So he was a newspaper tycoon. And he saw the profit in World Cottage. He obtained the meteorites, and he exhibited it just along the way in Piccadilly Circus in the coffee houses. Of course, charging admission to see the meteorite. And one of those people who paid admission was Sir Joseph Banks, who was at the time the president of the Royal Society and a naturalist. And he already had some of the Siena meteorites from the year before in his collection. And he immediately recognized that there were similarities between World Cottage and the Siena meteorites. And so he commissioned this chap, Edward Howard, who was a young chemist, and Louis Bonan, who was a French mineralogist, to do an analysis of both the meteorites that he had in his collection, including World Cottage, and terrestrial rocks, including rocks from Vesuvius. And what Edward Howard found in some of the first chemical analyses of rocks was that all those rocks that people had said had fallen from the sky all contained large amounts of nickel, much more nickel than he found in terrestrial rocks. And so it was clear that these rocks were different from terrestrial rocks and therefore had come from outer space. And that's when the science of meteorites, the science of planetary science, was first created. And an awful lot we learned about meteorites since then. But perhaps the most significant event, at least for geology, was in 1983. Because in 1983, a group of meteorites, the Shugotites, Narclites, and Shisignites, group of related meteorites, were analyzed for noble gases. They contain glass containing noble gas, and the composition of that noble gas was an exact match for the atmosphere of Mars as measured by Viking. These were also quite young rocks. They were as young as 160 million years. And that told us they must come from a large body, a planet. And so finally, we knew where some meteorites came from, that we had rocks from the planet Mars. So finally, we could study the geology, the history of another planet by studying its rocks. And that was the day that geology became not the study of the Earth, but the study of planets in general. So meteorites are very useful things for studying planets, studying other planets. So we want as many meteorites as possible. And we could sit and wait for them to come to us. So several thousand meteorites actually fall around the world every year. But most of those aren't observed well enough to be found. So unless it lands directly in front of you, you're not likely to find it. And this really demonstrates this. So about 70 meteorites of some size, so pea-sized upwards, should fall in the UK every year. And yet, there are only 18 meteorites known from the UK. And all this time, we've only ever found 18, despite all the ones that should fall. And the reason's simple, we have a very green country, a tiny little rock the size of a pea falls underneath a bush, who's going to find it? It's a very wet country. Meteorites contain some metal. They corrode weather very quickly. So a meteorite might not last more than 1,000 years. We're on a country where actually the land surface changes quickly. If you ever watch those archaeology programs, they're always talking about digging down to the Roman level, aren't they? They dig down 6 feet to get to where the Romans lived. The land surface changes so quickly that there's no time for meteorites to build up in the UK. And so we go other places and collect them. We go where there's very little water, so they last longer, where the land surface is very stable. So hot deserts are very good to collect meteorites. So a meteorite can last maybe 40,000 years in a good desert. But the best place on Earth to collect meteorites is the driest place, and that's Antarctica. So virtually all the water in Antarctica is there as ice. It's not there as liquid, it can't alter rocks. And we know that some of the ages of meteorites in the Antarctic, that they've been on Earth for at least 2 million years. So they can last for a very long time in the ice. It's quite fun to collect meteorites in the Antarctic as well. So this is me. These things are called snotsicles. I don't know why they call them that. And this, back in 2003, to give you an idea how many meteorites we can come back from the Antarctic with, we came back with 800 meteorites from a 2-month field season. So an enormous number of meteorites. Because we're most interested in the rarest ones. Imagine picking 800 rocks up randomly around the Earth. How much would we actually know about the Earth from 800 rocks? So once we knew these things came from space, and we found that some came from Mars, but where did the rest of them come from? Well, for a long time, it was believed that most meteorites came from the moon. That all ended with the Apollo missions. And I've been very specific about choosing this picture. I love this picture because you can see the soundstage in the background with the little lights up there. Because, of course, some people still believe that the Americans NASA never landed on the moon. So let's put ourselves in the shoes of NASA faking the moon landings right now. So all these scientists are telling you that meteorites come from the moon, and you're going to bring back rocks from your fake lunar mission. So you're going to bring back, aren't you, the most common type of meteorites. And when the lunar rocks came back, they didn't look like any known meteorite. In fact, they looked very much like rocks from the Earth. They were all igneous. This one, you can see these lovely vesicles in here. This is actually a basalt. And they had compositions slightly strange, but relatively similar to the Earth. So they were completely unexpected. So it demonstrates the Americans really did go to the moon. Also tells us that meteorites don't come from the moon. And the other possibility of where they came from was from asteroids. The only difficulty in the early 70s was understanding how they got from the asteroids back to Earth. So the asteroids are mainly between the orbits of Mars and Jupiter. So that's at least 300 million kilometers from Earth. You know, even to a geologist, that sounds like a long way. And when astronomers started studying the abundances of asteroids, they started noticing, and this shows the abundance through the asteroid belt. So Mars is just about there, Jupiter is up here somewhere. And you can see that there's these funny gaps in the asteroid belt where there's hardly any asteroids. And these are known as the Kirkwood gaps. And they're locations where Jupiter's gravity has much more effect. It's a form of resonance. And in these locations, asteroids are pulled out of the asteroid belt. And their orbits slowly change and move down through the solar system until they cross those of the planets. And so we had a way of delivering meteorites from asteroids to Earth. And so finally we knew that a lot of these were coming from asteroids. So what about their materials? Are these geological materials? Are they things we would recognize? Do geological principles apply to these minerals? So probably the weirdest are the iron meteorites, the big lumps of iron. Now, I remember when I was about 8 years old, I had this book of scientific mysteries. It's great. You know, I had things on giant squid. But one of them was on iron meteorites. And in the book, they claimed that iron meteorites had these really unusual properties. You know, the metal was harder than any other known metal. That they consisted of metal that couldn't possibly be made by humans. And there was kind of an inference there that maybe there were bits of alien spacecraft. All of that is complete and utter rubbish. So they're actually just made of iron nickel metal, which is pretty ordinary stuff. They contain some interesting minor phases like iron carbides, the mineral cohenite, iron sulfides, troilite, as opposed to pyrite or pyrrhotite, and then this rather strange iron phosphide, shrubicite. So all those minerals actually occur on Earth. Iron nickel metal is very, very rare on Earth because of our oxygen-bearing atmosphere, but it does occur. But what about this odd texture? So the texture is known as a Widmanstätten texture. And we can see that we've got lots of these these bands, and the bands consist of low nickel metal iron. It's known as kamacite. And in between the bands are high nickel metal iron. And that's known as tanite. And the bands grow as the metal cools. So you've got this solid lump of metal. As it cools, the nickel and the iron are really unhappy with each other, and they split into two different minerals. The kamacite bands start growing in the cooling metal. And that's a process called exsolution. And we see exactly the same process in minerals on Earth. So this is actually from a terrestrial rock. This is obviously a thin section picture, so it's taken with a microscope. And you can see that this grain here, this is a pyroxene. It's from an ordinary terrestrial gabbro. And these little bands in here are exsolution bands. It's where the pyroxene is unmixing into two different pyroxenes during cooling. So that process of exsolution is common between the Earth and wherever the iron meteorites come from. What is different, and this is where the book was kind of almost right, is we can't make metal that looks like this. Not because we lack the technology to do it, we just don't have the time. Because the cooling rate you need to make bands of this thickness is about 0.5 degree per million years. So you have to cool them extraordinarily slowly. So all the minerals in iron meteorites, even the iron we find at the Earth's surface, but very rare occurrences. But actually, in actual fact, iron nickel metal is a very terrestrial material because the entire core of the Earth is made out of it. You know, the inner and outer core are both made of iron nickel metal. And this is how we explain these really low cooling rates of iron meteorites, that they formed as the core of asteroids, and that the silicate mantle surrounding that core insulates it so it can cool really slowly. And in fact, you only need an asteroid about 30 kilometers across to make cooling rates that are low enough to make iron meteorites. A bigger group of meteorites are the Stony meteorites, those made out of silicate minerals, very similar to most terrestrial crustal rocks. And one group of those Stony meteorites are igneous rocks, so they've crystallized from magmas. And we call these the chondrites. I don't know why we just don't call them igneous, but there you are. But this is very obviously an igneous rock. You can see these nice big gas bubbles in here. These were vesicles, and all this material was crystalline. So here's a thin section picture. These are the gas bubbles, and we can see all these nice little crystals of pyroxene, and we've got the odd crystal of plagioclase in here too. So this is a pyroxene and plagioclase rock. And if you remember your mineralogy and petrology, that makes a basalt. This is a good old plain basalt. Basalt is one of the commonest rocks on the Earth's surface. It covers the entire ocean basins. The oceanic crust, the upper layer, is made of basalt. And so there's basalt on some asteroids. Basalts erupt in volcanoes. So there must have been volcanoes on some asteroids. So that basic process of melting, generating magma, transporting it to the surface and erupting it to make lava flows is common between the geology of asteroids and the geology of the Earth. And of course, we also know we have volcanoes on other planets. The most famous of which is Olympus Mons. So this is the biggest volcano in the solar system. And yet it's fairly ordinary. We can see that its slope is very gentle. It's a shield volcano. So very similar to Hawaii. And most of the Martian meteorites are actually basalts. Low viscosity, very runny basalt magmas that make shield volcanoes. There is a major difference, though, between Mars and Earth. And that's really down to size. So the Earth, being quite a large body, has quite complex internal convection and turnover of its mantle. We know that we have tectonic plates on the Earth that move relative to each other. Sometimes they will slip underneath each other, so we have subduction. and subduction helps generate volcanoes. And in fact, actually, it generates different kinds of rocks as well. So the vast majority of the world's granites are located at subduction zones. Whereas on Mars, there's no plate tectonics. There's a crust, but it doesn't move relative to each other. There's no subduction. So presumably, very few granites. And because it's much smaller, the turnover of its mantle is much simpler. There appear to be just two large plumes on either side of the planet. And above the top of those plumes are two bulges, the Tharsis and Elysium bulges. And Olympus Mons sits on the Tharsis bulge. So it's got a constant supply, it's had a constant supply of magma, possibly explaining why it's so large. So we can apply the general processes of planets, of melting, transports of magma, eruption of magma, building of volcanoes, is the same on two planets. But there are differences we have to take into account related to the size and subtle differences in composition. So let's look at whether the general principles of geology are the same between the Earth and those rocks that form on other planets. And this is the sort of stuff that most of us learn in our first year at university. So one of the principles is the law of superposition. Very simple rule of geology, formulated by Nicholas Stanner in the 17th century. So if we are generating layer after layer of rocks, say as layers of sand being deposited one after another, then the rocks at the bottom of that pile are the oldest and the rocks at the top are the youngest. So we can use that simple superposition, the order of rocks, as a relative dating. So does that apply to other planets as well as the Earth? Well, it certainly does, because this picture is actually not of Earth. This is Mount Sharp in Gale Crater on Mars, and that image comes from Mars Science Laboratory, from the Curiosity rover, which is currently driving around this crater trying to get to those rocks we can see in the distance to do a bit of geology. We can also use the law of superposition for impact craters, because obviously, if we're going to make an impact crater, the surface has to be there before we make the impact crater, doesn't it? We can't make the impact crater and then make the rocks. And that means that we can use the abundance of the number of impact craters to help us date the surface. The more impact craters the surface has, the older that surface is, the longer it's been around to accumulate impact craters. And in this really nice picture from the moon, we've got the edge here of the lunar highlands, which is all these light-coloured rocks, and the dark-coloured lunar mare. I hope you can see that there are many, many more craters on the lunar highlands. So there's about 10 times more craters on the lunar highlands than there is in the lunar mare. So using the law of superposition, we'd assume that that means that the lunar mare the lunar highlands are 10 times older than the lunar mare, which they aren't. And that takes us on to the next basic rule of geology, the principle of geology. A much maligned principle of geology, uniformitarianism. And Charles Lyell sort of popularized this. The idea was already around. He popularized it in his book, The Principles of Geology, back in 1830. And the key to this, you'll remember this if you've done geology at university, the present is the key to the past. So we can look at a process that's happening today, say the transport of sand on a beach, and then we can apply what we learn from that process to what we see in rocks. That process should operate in fairly similar fashion in the past. And what we're assuming when we look at this image and try and estimate the ages of the surface is that the impact rate stays constant. So the number of impacts with time stays constant. But that's not true. So we know from the lunar samples that there were a lot more impacts during this period between 3.8 and 4 billion years. It's a period called the late heavy bombardment, when the Earth and the Moon, in fact all the objects in the inner solar system, were peppered with impacts. And it just so happens that the lunar mare Lunar Maria formed between about 3 and 3.5 billion years. And they just post-date that period of really heavy bombardment. And so the point is that uniformitarianism works. The name is rather unfortunate because things do not stay the same. So we can use the present as the key to the past, but we have to remember that things can change with time. We can also use it to look at other planets. So this is a great picture from Mars Science Laboratory again from Gale crater, and all the geologists in the room have probably just got, oh, look at that in the middle, because here we've got these nice grey rocks, they're coarse-grained sandstones, and we can see there's cross-bedding in them. So you can see the banding in the rocks, and notice the way that there are truncations here, and these are curved surfaces. Pretty typical trough cross-bedding. And trough cross-bedding means deposition in water when the beds are at least at this scale. So by using uniformitarianism, by looking at processes on Earth today, we can interpret the past of Mars. So the present isn't just the key to the past, it's also the key to other planets, to interpreting other planets. But again, we've got to remember the differences. Gravity is different on Mars. So when looking at things like the size of crossbeds, in terms of the size of a river, a fluvial system, that we've got to be really careful. And actually, we can look at this series of beds. There's a whole load of trough crossbeds there. There's no what are called overbank deposits. So when a river floods, it produces these big mud drapes. There's none of those. So we can interpret a kind of river system. So there were probably braided rivers here. So these multiple channel rivers on Mars quite a few billion years ago in the Amazonian. So uniformitarianism really gives us a fantastic tool to interpret other planets. Another principle of geology, and don't worry, I'm not going to go through them all, was by Hutton, and it's the law of inclusions. And the law of inclusions states if you have an inclusion of a rock, so a piece of a rock contained within another rock, then that small inclusion must be of an older rock. So that inclusion must be older than the rock that contains it. Fairly obvious, really. And this is a really quite nice example of this, because the cream-coloured rock here is actually a basalt. And these are actually xenoliths within that basalt, so bits of foreign rock. And what this is telling us about is a story about a magma chamber. So we've got this nice big magma chamber, and crystals, dense crystals of say, olivine and pyroxene are forming in that magma chamber. And because they're dense, they sink in the magma. And then they start accumulating on the bottom of that magma chamber to make these big piles of crystals. They make a new rock at the base of that magma chamber. And then later, along comes another batch of magma. It goes through those cumulates, breaks them up, transports some of them up to the surface, and they're included in a lava flow. So does the law of inclusions also apply to other planets? Well, yes, it does. In fact, this is a Martian meteorite. Quite remarkably, one of the Martian meteorites contains xenoliths from a magma chamber. So what we're looking at is evidence for magma chambers on Mars. So again, we can use law of inclusions and uniformitarianism to interpret what's the geology that's happening on other planets in exactly the same way as we do on Earth. Now, so far, the geology in space has sounded pretty much like the geology on Earth. But there are some exceptions, because things are about to get really weird. Because the majority of stony meteorites are not igneous rocks and not crystallized from magma. We call them the primitive meteorites. And they are chondrites, and they're typified by these little rounded objects. They're only a few millimeters in size. And what's truly remarkable about these little rocks is their composition. Because when you analyze them, they have the same composition as the sun as a whole. So excluding the hydrogen and the helium and all the gases, the heavy elements they have exactly the same composition as the Sun. Well, within a factor of 3. And what's interesting about that is if we pick up any rock from the Earth, say a basalt, that has a composition really different from the Sun because it's been affected by melting and crystallization for billions of years. These rocks have never been changed from the basic material that made up our solar system. And therefore they formed before planets, and they've never experienced geological processing on a planet. In fact, we could, if we wanted, create a whole new principle of geology. Let's do that now. So the new principle of geology, and I'm following Lyell's example here by taking an existing idea, repackaging it, and claiming it as my own. So the law of chondritic compositions, rocks with a chondritic composition have not formed on geologically active planets. And let's call that, let's be generous, call it us. That's us, 2014. So what was the environment like here before planets? What did our solar system look like before those planets formed? Well, we can use uniformitarianism again. We can look at the present, because we can see stars and planets forming right now. So here is the constellation of Orion. And what we're looking for, the best place to find baby stars, is in a Mission nebula. And so these are in big molecular clouds, these big clouds of dust in space. And it's where you have lots of hot young stars, and the light they produce is reflected from the surrounding dust. And there's a good one down here at the bottom of Orion, at the tip of Orion's sword sheath. And if we zoom in on that area, we start seeing some really big, massive stars, and then finally we see the tiny little babies. But these are about the same mass as the Sun. And what we can see in here is a baby little star surrounded by a disk of dust and gas that absorbs all the light from the background. And these form when stars are formed. So gas clouds make stars by collapsing under their own weight, under their own gravity. And because those gas clouds are usually slightly rotating, as they collapse, they start to spin faster and faster and faster. And angular momentum flattens them out into a disk. And it's in that disk, once the dust has got all really close together, the dust particles start sticking to make larger objects, to make planets. And it's for that reason that all the planets go round in the Sun in the same direction and in the same plane, because they formed in a disk. So our solar system looked like this when these rocks formed. There were no planets, and these rocks, these asteroids, were forming in this dusty disk surrounding the young Sun. So we have to place our observations in that context. So let's start with the calcium aluminium inclusions, these little white grains here, quite irregular in shape. As their name suggests, they contain lots of minerals rich in calcium, titanium, and aluminium. And these are very high temperature minerals. And we think they form by condensation of a rock gas. So if you heat a rock up to maybe 1,900, 2,000 degrees Celsius, it will start to evaporate to make a rock gas. If you allow that gas to cool down, the first things to crystallize will be these calcium, aluminium, and titanium minerals. They'll condense out of the gas. Kind of like a mineral snow. And so the idea about the CAIs is that these form in the really high temperature regions of the solar nebula, of this gas cloud, at the inner margin close to the young Sun, where everything's really hot and being evaporated. And then somehow they get scattered outwards through the solar system, because we can now find them in rocks from the asteroid belt. And how much that scattering works is probably going to determine what final composition the planets are. So it's really important to understand. The other objects in this material are the chondrules, the beautiful little rounded droplets. And when we look at them under a microscope, we can see they look very pretty. So these are all olivine crystals, and in between the olivine crystals is glass. So these are igneous rocks. These were droplets of magma in space. So we need a way of melting little dust particles in space. And actually some of them, like this one up here, you can see have numerous rims around them. They've been melted more than once. So the most I've ever seen is a chondrule that's been reheated at least 5 times. So we need a way of continually reheating them as tiny little dust particles. And probably one of the favourite models at the moment is that these get heated in shock waves. So we've got a gas and dust cloud, and this powerful shock wave comes through, moving at several kilometres per second. And suddenly the dust particle finds itself in gas that's moving very quickly. And friction with that surrounding dust heats up the particle, and it melts to form a chondrule. So the early solar system was a very disturbed place. And we don't quite know yet how this heating up process changed the compositions of the planets. Final piece of these chondritic meteorites is the matrix. It's really fine-grained stuff in between the chondrules. And this is really fun stuff. It's very fine-grained. So here's a scanning electron microscope image. And this scale bar is 5 microns, so 5 millionths of a meter. And you can see that a lot of these grains in here are less than half a micron in size. That's tiny. These little olivine grains. Even in a mudstone on Earth, a lot of the clay particles are bigger than the fine-grained material in here. But what's really truly remarkable about this material is the stuff it contains. Not terracotta soldiers, although that would be fun, I must admit. They contain clay minerals, so the stuff that makes the terracotta, which means they contain water. So some of these meteorites contain 15% water. They're effectively balls of mud. And we think that water came from ice that was on the asteroids, and that ice melted, generated water. We had minerals like olivine around. Olivine really doesn't like being around water and gets transformed to clay minerals. There's also organic material. Not coal, really, but hydrocarbons, amino acids, and even sugars. So there's organic molecules sitting in that very fine-grained material. Now, of course, most of us will equate this with life. We know that coal comes from carboniferous coal swamps, most commonly from carboniferous coal swamps. But this has nothing to do with life, because it's possible to make these molecules in the depths of space. So out in the giant molecular clouds, these big clouds, they contain lots of organics. We have small little dust grains on which the organics condense as an organic ice, and then the ice gets irradiated by the light, the radiation from stars. And as soon as you start irradiating dust grains that contain organics, that starts doing all sorts of weird photochemistry. You can build some really big, complicated molecules. So there's actually geology involving rocks, dust grains, going on in these big floating clouds in space. And the particularly interesting thing about the presence of organics and water on these primitive meteorites is it provides a way of delivering water and organics to the early Earth. We know that building a planet is very hot work. By the time, it's very difficult to actually build a planet quick enough without melting it. And of course, as soon as you start melting it, you start losing those organics and you start losing the water. And the delivery of organics and water during the late bombardment is currently thought to be the explanation for how the Earth got its oceans and for the organics that would lead to the origins of life. And organics in exactly the right form, so including amino acids. Finally, we've talked mainly about meteorites, but there is other stuff that falls through our atmosphere in the form of dust particles, the cosmic dust. And I'll talk about this just because this is my actual research area. And we get about 40,000 tons, actually, of dust from space falling through our atmosphere. That's an enormous number of particles, so there will be cosmic dust in this room. Many of you will have cosmic dust on your clothes. Doesn't mean you're dirty or anything, you just have that on your clothes. And most of those particles actually look like bits of asteroid. So if you took a meteorite and broke it into bits with a hammer, that would pretty much look like most cosmic dust. But there are some very rare ones that are very porous, contain so olivine crystals, pyroxene crystals, stuck in this matrix of organic glue. And that's very similar to the description of comets. So astronomers think that this material is derived from comets. Comets produce enormous amounts of dust as they heat up in the sun. The ice turns into gas, the gas streams away from the comet and takes the dust with it. So we can actually use cosmic dust particles to study comets, which we can't do with meteorites. Comets are very fragile. Getting them through the atmosphere as sort of bag of sugar-sized things isn't really possible. What I personally really like about cosmic dust is that it's probably some of the fastest geology on Earth. So when they hit the top of the atmosphere, they're going at least 11 kilometers per second. And if they're moving vertically, the atmosphere gets very thick very quickly, and they can heat up and melt. And this image kind of shows that procedure from an unmelted particle. It starts melting and getting gas bubbles, gets more melted, more gas bubbles, and then it loses its gas bubbles and turns into a nice little sphere. That process takes less than 10 seconds at least 11 kilometers per second. So I like to think of these as the fastest forming rocks in the world in both senses. So just to finish, perhaps the most fascinating thing in meteorites and cosmic dust are these tiny little grains that have very unusual compositions in mineralogies. So they include things like silicon carbide, there's tiny little diamonds, there's corundum. And the weird thing about them is their compositions, their isotope compositions, are very different from our solar system. In fact, so different from our solar system that there's pretty much no way they could have been made in our solar system. The only way you could make them, the only place you could make them, is where you make the isotopes. And where we make isotopes, one of the places we make isotopes is in giant stars. So these stars, the isotopes are made in the core. That core, through convection, takes material up to the envelope of the star, and at a late stage, when they become asymptotic giant branch stars, red giants, they start pulsing and they lose lots of gas. And imagine this gas streaming away from the star that contains silicon and carbon, and it starts to condense as tiny mineral grains. So there are rocks forming in the atmospheres of giant stars. There's geology going on in the atmosphere of a star. There's also geology going on when stars die. So when these big stars reach the end of their fuel supply, they collapse inwards on themselves, and then they explode to make a supernova. And in that supernova, we make most of the heaviest elements. In amongst these streamers, that gas is condensing to make mineral grains. And we found these supernova mineral grains sitting in amongst meteorites. So we've got to say that geology has really changed a lot. So we have to say that geology isn't just the study of the Earth. Geology is the study of planets, of asteroids, of comets, even of this stardust, of giant molecular clouds, of stars and supernovae. That doesn't really strip off the tongue very well. So it's easier to say that geology is just the study of anything in the universe with rocks. That leaves us with just one problem. We've only gone and called our science the wrong thing.
Well, thank you very much, Matt, for the very intriguing talk. Can I ask you something about the elemental composition of those Martian, the Martian meteorites that you talked about, the nickel, iron? Are there any other elements that are actually missing that you'd expect to see?
No.
What else can you derive from the elemental composition?
As we all know, there's not much room left in the periodic table for new elements. The only room that's left is in the really big ones that are really unstable and don't last long. They're a fraction of a second and they're gone. The only thing that we see in meteorites that we don't see in terrestrial rocks is unusual isotopes. So things like beryllium-10, for example, we see in a lot of meteorites, but on Earth, beryllium-10 is produced in the upper atmosphere by the collision of galactic cosmic rays with oxygen atoms that make beryllium-10, and it only lasts a few million years. And that beryllium-10, you can actually trace it from the upper atmosphere into ocean sediments. There's a lot more beryllium-10 in ocean sediments. There's hardly any in the oceanic crust. And then it subducts, and we even see some coming up of volcanoes. But there's loads in meteorites, because the meteorites are exposed to radiation in space. And actually we can use some of these we call them short-lived radioisotopes, so they decay very quickly. There's a whole suite of them. We can actually use them to date almost exactly when a meteorite lands. So some of them decay in hours, some in weeks, some in months. And we've actually used this because some people work out that if you see a meteorite fall in front of you, it's worth a lot more than if you buy it on eBay. And so most of them don't realize that we can actually tell when a meteorite fell by analyzing the short-lived radioisotopes. So we have caught a few people out.
Very intriguing. Questions from the floor? There may be some microphones.
If cometary dust is so fragile, how do they collect it?
This might not sound like the most gentle way of collecting it, but you know those U-2 spy planes? So they fly along 40 kilometers altitude, and they've got these really odd collectors that sort of stick up out of the wing. They're sort of motorized, they come out of the wing at altitude, and then they run into plates covered with silicone oil. But they're so tiny, so that most of those are about 15 millionths of a meter in size, that frequently actually breaks into pieces when they hit the plate, but you just get a whole load of them together. It was much more of a problem in space, so we tried, as part of the Stardust mission, collecting dust actually in space by flying through the tail of a comet. Well, not me personally. The spacecraft flew through the tail of the comet. And the problem was the spacecraft was going to hit the dust particles at about 6 kilometers per second. So we needed a way of really slowing down the particles without heating them up. And they devised this incredible stuff called aerogel. It looks like solid smoke. You know, you hold it in your hand, you almost can't feel it. It's amazingly low density. But they actually managed to stop dust particles traveling at 6 kilometers per second in a couple of centimeters. Unfortunately, that did cause quite a lot of heating. So that limited what we could get back from that mission.
Hi, two quick questions. The amino acids you find in carbonaceous chondrites, are they racemic or are they handed?
Yeah, they're racemic.
And the second question is, I've been rereading Watson and Lenton's Revolutions That Made the Earth. And they do mention the late heavy bombardment and the late veneer. But they also refer to zircons forming 4.2 billion years ago that were hydrated and formed in a marine environment. So, I mean, it seems to be contradictory if you follow my drift. Did the late veneer bring all the water and stuff to the Earth? Or?
There is a lot of work going on at the moment on exactly how much water the Earth had prior to the late bombardment. So it's actually very difficult to keep water around in the inner solar system at all. So most of these hydrated asteroids come from the outer asteroid belt. The objects that we believe started off around the Earth are all igneous objects and contain very little water. And what happens when you heat up an asteroid is it loses its water, because that's when they get heated up, when they're really small. It loses its water and a lot of its carbon into the gas phase surrounding it, and then that gas phase gets blown away by the wind from the sun. And so there's a real problem keeping volatiles around the inner solar system. So at the moment they're talking about things like the amount of water that you can absorb on the surface of a mineral grain, which would seem to me not to be enough to make the Earth's oceans. But it's entirely possible that there was at least some of the Earth's budget was originally present during accretion of the Earth. But I think you need a lot more. And it's kind of suspicious that you know, the first evidence for life is straight after that late heavy bombardment, and yet you've got biologically relevant, if not necessarily exactly the right ones, biologically relevant amino acids within meteorites.
Yeah, on that late heavy bombardment, could an explanation of that be that there was a planet in the asteroid zone that broke up, that gave rise to this late heavy bombardment?
It's very difficult to say because we really don't have samples from the late heavy bombardment. We've got some signatures within some of the impact craters. So it looks like they're chondritic bodies. But every couple of years, I've got to be careful not to say anything nasty about astronomers. Every couple of years, astronomers come up with a new explanation for what the late heavy bombardment was. So quite a few years ago, it was that when Neptune finally got to its final size, it starts really disturbing all the icy objects that are around it. Some of them get thrown out of the solar system, some of them get thrown into the solar system. And we know that happened. We know that definitely happened. We know that Neptune got to its final size maybe 600 million years after the start of the solar system, which is about the right time. But whether it could produce that spike in impact is the question. There's been some suggestions that Mars moved outwards a bit and started disturbing the inner belt asteroids. But that's a problem because they probably didn't contain much water. So there's many suggestions about why it's been. I don't think anybody's convincingly come up with a reason.
That distance, that planet, it would be further out, but perhaps at the time it was in the Goldilocks, so the sun was hot at the time.
I think it would be difficult to fit another planet in the inner solar system because the planets have got certain feeding zones which they need to get to full size. And we certainly know we lost that some of the objects in that zone in the inner solar system were lost. So, for example, the idea from the Moon is that there was a giant impact with the second largest object in the Earth's feeding zone. So, imagine the Earth growing. The Earth is the biggest object. Then there's another object that's maybe the fifth of the size of the Earth, and then there's a whole series of objects that are smaller than that. And that's what's left after you build planets. So there's the Earth going round and round in its orbit with another object, which is a significant size, and eventually it's going to run into it. And that resulted in our Moon. But we know a lot of the other planets also experience big collisions. So Venus, for example, goes around the Sun in the same direction as all the other planets, but its orbital period, it's really strange, it actually orbits, its rotation is the opposite sense of all the other planets. And the idea is that was a giant impact. So where's that impact gone? So there was a lot of stuff thrown either into the Sun or out of our solar system.
I'm quite intrigued by the similarity between the basalt, Mars basalt, and the terrestrial basalt. So I'm wondering if we find other similarity apart the composition and the xenolith, like some zoned minerals, or the condition are not that they cannot be preserved, or it's all homogeneous.
So Cara is a petrologist at the Natural History Museum, you can tell. The similarities, there's the broad similarities in mineralogy. They are transitional basalts, so you can split basalts up to tholeiitic basalts and alkali basalts with transitional in the middle, depending on the amount of sodium and potassium that they contain relative to silica. So they are sitting in that boundary in between the two. When you look at their trace elements, they look moderately depleted to enriched. So there's I think there's two groups. There's a depleted and enriched group. So the idea is that there were mantle plumes at some stage on Mars. But just ask Caroline. She'll show you all the meteorites. Excuse me.
How do you quantify the amount of cosmic dust falling on the Earth per annum?
That's a good question. I sit there for a long time. It actually works out to about one 100 micron particle per square meter per year. So you could die waiting, it's a dull process. The way it's actually been measured was from the Long Duration Exposure Facility, which is a fancy name for a satellite that was flying in orbit for 5 years. And when micrometeorites hit satellites, they make little holes, little craters. And so what you do is you count the number of craters per square meter, and then you correct for the gravitational acceleration as it comes down the Earth's gravity well. And the result we come up with is about 40,000 tons per year, plus or minus 10,000 tons. Roughly,
You did mention two processes by which water has been transported to this planet, but the current theory, or the main theory, seems to be it comes from comets. How on earth can even a massive comet invasion on this planet produce so much water?
Well, comets, there's a lot of water on comets. So comets, in terms of mass, are at least 50% water. So you don't need that, you only need double the mass of the oceans. But the problem is that so far we haven't found a comet with the right kind of ice. So we've been looking for the oxygen isotope composition that matches the Earth's oceans. And so far, no comet has the right composition. There's a few asteroids that get close, but nothing seems to have the right oxygen isotope composition to make the Earth's oceans. So that's a really big question. Where do the Earth's oceans come from? It's entirely possible. We've lost so much stuff from the solar system. So it's a remnant of its former self. Most of the material was ejected from the solar system. That we've lost most of those original icy planetesimals. That's the fancy word for comet. That originally hit the Earth and added the oceans. It'd be very interesting to see if we can find what the isotopic composition of Mars's oceans were. Was that the same as the Earth? That's a big question.
So NASA seems to be focusing a lot of their sort of space flight thing on this potentially wacko plan to go and find an asteroid and capture it and bring it into an orbit around the moon so that we, I suppose, can explore it. Is that a feasible and B useful thing to do?
Well, I don't think that's NASA's main plan. Last time I talked to those chaps, their main plan is Mars still. They've got a secondary plan about building a moon base, and probably don't have much time for dragging asteroids around. There's certainly some companies at the moment that are looking at mining asteroids. So they're putting a lot of money into this. And the idea is that it's so difficult actually to get to asteroids that it's really not economically worth doing it, because anything you bring back, if it costs so much to get there, it's just not economic. So one of the ideas is you drag an asteroid back and you park it in Earth orbit. So it's going round and around the Earth. That would seem like an incredibly stupid and dangerous thing to do, because I'm terrible at parking. And I don't see that ever happening. It's just too much of a hazard.
What is the biggest potential benefit that could come from all this research that might be transformational for humans, that might stem from all this area?
Well, it depends very much I guess, your personal opinion on what's transformational. So I could talk about mining of asteroids. So, for example, one of the up-and-coming technologies that kind of works, but doesn't work well enough yet, is nuclear fusion. There are fusion reactors. They just require more energy put in than they get out at the moment. But if they eventually make that work, the clean nuclear fuel that you need is helium-3. It doesn't produce any stray neutrons, so you don't get any radioactive waste from it, and there's very little helium-3 on the Earth. there's loads in the lunar soil. So mining the moon, for example, to get helium-3, if fusion reactors eventually work, will be really well worth doing. But then on a sort of a less economic note, I think probably the biggest thing that planetary science could do is demonstrate there's life elsewhere in the universe, because that has such fundamental implications. You know, if we are not alone in the universe, if we find life, for example, on Mars, it tells us that the origins of life are spontaneous given the right conditions. That's something we're just not in the position to say at the moment. If we find two separate sets of life in one planetary system, the chances that the universe is filled with life become astronomical. You know, it probably won't change the way we live our everyday lives, but...
One more question from the gentleman, well, two then. The gentleman there and one here.
I believe the Rosetta mission is going to land on a comet nucleus this year. That's a great achievement, but there must be some scientific benefits to all of this. Would you like to comment on what the scientific achievements from this landing might be?
So Rosetta is flying to a comet, it's going to land on it. There's many things we don't understand about comets. Unlike asteroids that we can observe, we can fly past them, we can point a telescope at them, we can see the surface. With comets, you usually can't see the surface. It's embedded in the coma. So there's lots of things we need to know about comets. Like some comets appear to turn into asteroids. So they just stop producing gas, and then they go dark, and they look like asteroids. And we think that over time, they're firing off lots of gas, that this layer of debris builds up on the surface, this mantle, starts cutting off heat from the ice below, and they start looking like asteroids. And so if we've got an object, say, that's on the way to Earth, it's going to hit us, we really want to know if it's an asteroid, if it's a high-density asteroid, or it's a low-density comet. And if there's these asteroids out there that contain loads of ice, then maybe in the future we need to know that if we're going out into space and we're mining. We don't know exactly what the composition of comets are. We've seen there's a lot of variation, especially in the gases they produce, in whether they produce water vapor, how much carbon dioxide they produce, how much carbon monoxide gases they're producing, and what the variation in the organics are. We just simply don't know.
Sorry, I wasn't going to ask this one, but your answer before last gives me confidence. Panspermia, just a crackpot theory or perhaps something behind it?
Panspermia, lovely place. Panspermia is a really weird one. So the idea is that life can be transported between planets on meteorites. So you blast a rock off of one planet in an impact. It contains a microbe. Microbe survives the trip and then gets to the other side and goes, well, hey. And it's not as stupid as it sounds, because if you pick up virtually any rock on Earth, it's going to have microbes on it. It's virtually impossible to keep them off of rocks. So even meteorites picked up in the Antarctic, we find microbes on them, and usually they're the kind of microbes that people have on their hands. Yeah, they're from human beings, so we're pretty confident they don't come from outer space. It's just contamination. So the chances that a rock is blasted off a planet, if the planet's got life on it, it's probably going to have microbes on it. The question is, can they survive the journey? Can they survive the radiation in space? Can they survive the accelerations? So there's been experiments that have been done on survival, and certainly certain microbes are very resistant to radiation. So radiation in space, they can handle that, they can repair themselves. They can turn into spores, which last simply forever. You know, microbial spores last hundreds of thousands of years. There was a very interesting study that tested how microbes deal with acceleration. And it was a great little example of brass tacks research. So what they did was they got air rifle pellets and they painted bacteria on the back of them, and then they fired them at, well, presumably a PhD student. And what they found was they got a 400% yield, because this particular microbe was multicellular. It had 4 cells, and it hit the wall, it broke into individual cells, which then all split and made new bacteria. So bacteria seem to handle very large accelerations very easily. So it's certainly possible that it could happen. And I know what will happen. So if tomorrow Mars Science Laboratory discovers a green pile of algae on the surface of Mars, the very first objection that will be made will be, well, maybe that came from Earth. And that's where the difficulties will lie.
Right, well, I think we'll wrap it up there, ladies and gentlemen. It just remains to say... Thank you very much, Matt. It's been a very wide-ranging talk. We've heard some really interesting ideas. I've heard a lot of really new things that I hadn't heard before, and you've illustrated a huge range of research that still needs to be done in various areas. So good luck with your future research.
Thank you.
And, I hope you find many more things of great interest. Thank you very much. Ladies and gentlemen, we have a reception, short reception, and you're all very welcome to join us in the lower library next door, and Matt will be there, hopefully, to answer some more questions.
Yeah.
Otherwise, our next meeting